We're going to talk about the OSI 7-layer model. And although it is a model, in other words, you can't go out and buy it and see the real thing, it does map quite nicely to the real situation. The OSI 7-layer model needs some way to try and remember it. And the way I remember it is all people seem to need data processing, because I can never remember it. And those are the first letters, the layers of the model. Processing physical, data link, need for network, T for transport, S for session, presentation, application. There we go. This layer dates back a number of years, and it's used to apply the way that stuff is sent along wires or through the air to send a message from one machine to another. Oddly, the method that we use, TCP/IP, which is what most of our modern machines use these days, and the internet tends to use an awful lot, is not quite the same as this. This model is designed to represent any vague, non-existent system, but the TCP/IP model is one that we use genuinely on the wires. Now, when we send data from A to B, we encapsulate it. Various fancy words. One was in a packet, so we put inside our packet all the stuff we need to know. We can look inside the packet, and then we can see inside it the existence of some parts of these layers. But because the packets we use are TCP/IP packets, and this is a general, wishy-washy, top-level, vague description of things, not all the bits are easy to see, but some are fairly straightforward. If we start off with a physical layer, you can't really see that. Well, I suppose you can, but in terms of numbers, zeros and ones, we can't. It's the actual transmission medium, the thing that takes stuff from A to B. It could be a wireless waveform taking it from A to B. It could be an Ethernet cable. Now, as well as the actual cable or the wireless thing itself, is the way we encode on that particular cable. So if it was sending zeros and ones down a copper cable, or flashes of light down a fibre cable, it's saying, well, how bright a light is a zero light, and how bright a light is a one light. At what point is a light a 0 or 1, or is it just saying it's just a fluctuation in the environment or the cable? At what point is it saying, okay, these are just random fluctuations, and my message is about to start, so hang on, wait for a message coming, look out, message coming, here's the message, start listening now, and then message stopping, and gap. Because if we imagine inside our cable, or light, or whatever, if we're constantly transmitting, at what point do we stop one transmission and start another? Is there a little gap somewhere between one packet and the next? Or is there actual trailer and header to it saying packet coming up, and then read the packet and then stop? This is what the physical layer is getting on with down here. That particular bit is the encoding on the transmission medium. The data link, simplest thing to describe it over here is the Ethernet or the MAC. Now, this is what's actually going on. We've got on our machine somewhere some sort of card, wireless card or a physically hardwired card or something like this. And in that particular over there, it's got a number on it. And that card's got a particular number given to it by the manufacturer and when it was made. So this is saying, okay, from this machine to that machine, we've got a way of identifying a particular machine. We're going to move from place to place like that. This is a great system and it works, but it's not very flexible, because if we assume that every machine's got a number, which it has, or we give every machine a name, there's no logic to it. There's no working out what's going to go on where, and who's where and who's what. We need at some point to give things a ordered system. some system of numbers or names that make sense. Take this the internet, things have got like .com, .uk or whatever. We've got an internet number, machines assigned a number, there's a pattern to the numbers. So within our particular building, our numbers exist within that pattern of IP addresses basically. The data link layer doesn't care an awful lot about that. It just moves it from A to B. Some early systems didn't bother with IP addresses. Some years back, it wasn't just IP to move stuff from A to B. There was Apple Talk, which I've never ever seen. There was a Microsoft thing called NetBEUI, how it worked, it seemed to work, whereby you could have a machine on a Windows network advertised and sharing stuff, and other machines could see it. And they weren't using IP addresses. There was a system called Novell. Novell still exists, of course. But they created a technology called IPS SPX, which is a kind of way of identifying numbers of machines. A machine with an IPX SPX number or an IP number. It didn't like having both at the same time. So you were stuck with this. But basically, that's the boiled down bottom layer to it. Now, up here, we might have an IP address. So these two, a machine will have generally two addresses. You can have more than one address. You've got other things based on it as well over there. So we can take a machine and give it inside our machine code or operating system a number. It's also got the number that was given to it when it was born, when the network card was built. So if I've got a machine with two network cards and a wireless card, it's got three numbers like that. If I attach one of those cards to an ISP, internet service provider somewhere, then it's going to pick up a number from that ISP number, a network number over there. And that's going to be something like, I don't know, 172.16.34.7 or whatever. And the ISP can track those numbers and make sense of it. Stop there. You would see it almost like this. So you would see some data link information, and inside that would be some network information, and later after that might be some transport and so forth. So all this information is written like a book. Read this, read that, I'll go up here, read this, read that, read that, read that, read that, read that. And in the very centre is the application layer information, which tells what we're actually going to do with something. Data link layer, physical address of the card. We can spoof a card's address. So just because your card's got burnt onto it, a particular address or number, we can make it pretend to be a different number. But we're not supposed to, but you can. The network addresses are set in the machine's operating system, which could be a local one, or could be a remotely booted one, or whatever. It could be assigned from somewhere. So many machines have a dynamic host configuration protocol server. When they turn on and do whatever they've got to do. They go and look or find some machine somewhere else, and that assigns it an IP address. The advantage of that is, if I've got a network of, say, 500 machines, if I give each machine a physical IP number and I mess it up and give two machines the same IP number, they will clash and the network won't operate properly for the pair of those machines. If I have a server that doles out the numbers as you need them, then we can assure that no two machines have the same number. Basic principle behind it is that a machine is lent a number for a certain number of hours or a certain number of days. And then if a machine isn't activated over a period of time, the number is given to a different machine. When that machine boots on again, it's given another number like this. The numbers are nicely routinely done. It's a bit slower, to be honest. So your absolute core machines, the crucial stuff, your web server, your email server, perhaps your proxy server, anything crucial in the network is given a fixed address. And the ones who just sat there, basic workstations, just access the internet, move some files about, give them a dynamic address each time they turn on. That way they're going to not be bothered on a fixed address and they'll work okay and it'll be fine. But it's a little bit slower to ask the DHCP server for what the number is and what the name is than giving it a fixed number inside the machine. But it's more convenient and you can't cock it up, basically. Transport layer Having got an IP address, we're going to pass that address off to something and do something with it. We come towards the concept up here of ports. At least for TCP IP we do. So this is good for TCP IP. We do a whole lot. And that works. And that works. But up here, in fact that works. These start to merge with TCP IP, but they come the same basic plot of them. If I've got something that's sent into a machine, it comes in through the network card or the wireless aerial or whatever as a load of zeros and ones with stuff inside it. Now that could be a web page come down from the web. It could be an email message to be sent to my email server. It could be an FTP file to be sent to open an FTP client somewhere. It could be almost anything. In comes the poor machine, load of zeros and ones. We can work out from here where it came from. What the heck are we going to do with this? What do I do with it? We go up and look at what the port is. There are well-known traffic. Somewhere inside it will say what port number it's destined for. And based on that, like port 80 is HTTP. The machine will look at the packet, read it through, and say, okay, if it's this, I'm going to do the other with it. Take my time and pass it on and do the right sort of process with it. That's what that's going to do. Another function of this layer up here is how I break apart the files. I've got a very, very large file. It's not going to be small enough to send us one set of information from A to B. So I'll break it up to smaller bits and send those smaller bits down through the wires or whatever. The other side then will reassemble. This links slightly with the session. Now I'm deliberately going now. In these layers, network, it's obvious what this is, but network starts to merge with transport. Because if you've not got any ports, you can't really pass between the network and where you're going to send it to. Transport and session, I'll use the word Windows, although not Windows as in Microsoft Windows. The TCP model starts to make this jigger a bit. It's not quite so neat, not quite so clever. The basic concepts are there, but the boundaries start to fall apart. There is definitely a boundary here, data link to network. No worries, we can see the MAC card, we see the IP card. We don't mention the physical because it shouldn't matter. This is when I send something to the internet, does it go through my wired Ethernet port? Does it go through the wireless card? Generally the machine just doesn't care, it sorts it out for us. But here the boundaries start to blur. If I'm taking a message and breaking that message up to lots of smaller messages, imagine for example you're downloading some film off the internet. It's a great, huge, whacking, great big film. That's not going to fit in one Ethernet packet. And if it did, the Ethernet packet would take forever to get from A to B. It'd be a great, huge, long thing. It sends lots and lots of different packets. Someone at the other side has to stick them all back together again. Has to work out which packet comes in which order and then work out, okay, this is my film and it's going to be okay, we can play it like this. What can I get away with? And this is the concept of Windows, and in fact sliding windows, it wouldn't fit inside a tiny box. So we can split up a conversation, if you wish, a computer conversation, into these individual bits, send them along from A to B, and we can ensure when it gets to the other end, we can assemble them together again. What if it goes horribly wrong? Things do go wrong. The whole point of TCP IP is it's going to work. It's successful because it works. I didn't say it worked well, particularly clever. There have been some very nice network systems. You may have come across Token Ring. There's no point having a lesson on it. Basically, Token Ring was a brilliant system, and it would ensure you could pass things around from machine to machine, and it all worked tidy. Token Ring ran various speeds, like 16 megabits per second. Ethernet overtook Token Ring because A, it was cheap, B, it wasn't licensed to IBM protocols and IBM concepts, and C, it was faster. The basic user of the PC or the maker of the PC or the Mac or whatever